Didn't see you there. What's going on, fellas?
Nothing, G. We just here straight chilling with this Atwood machine.
For real, cuz. What's it do, homie?
So in this lab, the purpose was to determine the theoretical versus the actual data for an Atwood's machine, which is a pulley with two weights on either side that looks something like this. And we would label our two masses M2 and M1, which is really doesn't matter which one's which, it's just for notation. And then here we have a pulley, which we assume is frictionless and massless. So then, to test what the results were when we compared the theoretical and the actual values for an Atwood's machine, we first hypothesized that the theoretical value would be higher than the actual value because the theoretical value doesn't take into account factors such as friction or air resistance. So to test this, what we did is we took two masses. And so our masses were M1 it was 0.2 kilograms and M2 was 0.1 kilograms. So we found the theoretical values using our equation sigma F equals ma, which is Newton's second law. So after that, we constructed an actual Atwood's machine, and we used that to find the actual values by using a meter stick and a timer. So after that, what we did is we found our data, as you can see here, and then we found the percent error by using the percent error formula, which is the percent error equals the absolute value of the theoretical minus the actual value over the theoretical value times 100%. And so by doing this, we found that our hypothesis was supported by this data, and the theoretical value will be higher than the actual value if our data here supports the trend of all data that could be collected.
That's sick, but why?
Our setup is essentially a general vertical Atwood's machine with a 1.1 kilogram mass on the left and a 0.2 kilogram mass on the right. And we're going to measure the tension in the string and the acceleration of the system. This applies to Newton's first law, as there will be constant acceleration throughout the entire motion of the system because of the forces acting on each of the objects. It applies to Newton's second law because the net force will equal mass times acceleration, as we will see in our calculations, using T minus mg equals ma, as T minus mg is our net force. And it also applies to Newton's third law, as the force of the string, the tension of the string against the mass of the kilogram is equal and opposite to each other.
Sick. Let me see how this shizzle works, you feel?
Nah, bruh. You first got to know how it's built.
Ah, no way. I'm really feeling
Yeah, you're feeling it. Check out these calculations. So for our theoretical calculations of T and A, we first have our experimental setup of the Atwood's machine, with the 0.1 kilogram mass on the left and the 0.2 kilogram mass on the right. And we have the associated free body diagrams showing the forces of tension and mass times gravity. Then we can set up a two-system equation like this with the two different free body diagrams, and plugging in the known values, we can come up with this sum for the system, which gives us our acceleration of 3.27 meters per second squared theoretically. And then with this, we can use one of our equations to find the tension of the string, which would be 1.31 newtons. Then we can move on to the actual calculations that we got from our experiment, as each of the masses traveled 0.5652 meters in a time period of 0.61 seconds on average. Using our kinematics equation, we can find that the acceleration of the system was 3.04 meters per second squared. And thus, the percent error can also be calculated as 7.04% error.
Oh man, I'm learning a lot today.
We're just getting started. Here's our analysis.
It's mad tight, bro.
So as Hari pointed out, the theoretical acceleration is 3.27 meters per second squared, whereas the actual or experimental acceleration is 3.04 meters per second squared, yielding a percent error of 7.04%. Now, what this means is that our actual value was 7.04% less than the theoretical value. This makes sense if we think about it, because the theoretical value does not take into account other factors that may exist, like friction or air resistance. The way we found our actual value relates to Newton's second law, which says that the sum of the forces equals ma, which I'll write here for you. So this is how we found it, because what we can do is we can plug in ma equals all the forces. So we're going to have tension, and then we're going to have gravity, which is mg. But because they are going in opposite directions, either the tension or the gravity will be negative. As Hari pointed out earlier, the theoretical tension is 1.31 newtons. Now we are going to find the actual tension. Using our equation ma equals T minus mg for the 0.1 kilogram mass, we can rewrite this as T equals ma plus mg. Now, plugging in our values from earlier, we can get that T equals 0.1 times 3.04 plus 0.1 times 9.8, which you can just happen to know offhand like I do, equals 0.128 newtons. So now, we're going to find the percent error in our tension. What we need to know is that our theoretical tension was 1.31 newtons, and our actual was 1.28 newtons. So what we're going to do now is we're going to take our percent error formula. So our percent error formula is the absolute value of the theoretical minus the experimental or actual value over the theoretical value times 100. So here, our percent error is going to be TT minus TA in absolute value over TT times 100. So we can plug in our values now, and we'll get 1.31 minus 1.28, remembering our absolute value symbols, over 1.31, and then this will all be times 100, which we can just know offhand is 2.29% error, which means that because the theoretical value is greater than the actual value, our accepted value is 2.29% times 2.29% larger than our actual value from our experiment, which again makes sense because we're not taking into account other factors like friction or air resistance, which may play a part in the movement of the Atwood's machine that we ignore with our theoretical calculations.
Alright, time to wrap this up. I can get out of here.
Alright, 16 spin.
Catch you on the flip, homie.